Cool. Welcome to section. I'm not going to go through these each time, but we talked about last time how I've just kind of outlined the lecture and given you some explicit things that you will need to know. Yeah. Cool. So game plan for today, the big kind of topics that we're going to work through and talk about are functional groups. Then we're going to go to MO theory, molecular orbital theory, and talk about those frontier molecular orbitals and reactions, which you're going to be using a lot going forward. Then we're going to do acidity, and then the last 15 minutes or so, we're going to do one of the extra challenge problems, which are kind of like exam level problems. Any like logistical questions? I have one more announcement, and that is for especially Harvard students, y'all know about the ARC, like the free tutoring during the semester. So there's a summer version of that called the Academic Tutoring Program. I mentioned it last time. I was like, I don't know if they actually have tutors. They do. So there's free tutoring available for this course through the Academic Tutoring Program, ATP. If you Google that in Harvard, then you'll find the thing. So, work. Okay. So let's start off with functional groups. So functional group of atoms that we are going to use to help recognize patterns in molecules. And specifically, they're groups of atoms that react in certain ways. And so that's why we care about them. This chart right here, like this part, not the bottom part with the dashed lines, these are the ones you're responsible for knowing and will be an exam question to ask you to identify them. The exam question will look like this one, which we're going to do in a bit, where essentially we'll give you a crazy molecule and say, circle all the functional groups. So that is just straight up going to be part of an exam question. So be prepared. Let's talk through some of these. So I tried to group them into little families to make them easier to organize rather than just like presenting a bunch to you in a row. But still going to be a bit of a slog. So welcome to the slog. So here you'll see some R's. When I say an R just means something. Typically it's a hydrocarbon, and specifically when we have it in these functional group diagrams, it's some kind of carbon, and it could be like a methyl or an ethyl or propyl or isopropyl, whatever. We don't really care. We care about the part that's not the R. That's going to be the interesting part. That's the functional group. So when you see something like H/R, that means this could be an R group, like a carbon thing, or it could just be an H on. So if that becomes confusing as we keep going through it, then ask a question, I'll clarify. So if we have hydrocarbons on either side and we just still have hydrocarbons where everything is single bonds, then we call it an alkane. If we have a carbon-carbon double bond, it becomes alkene, and triple bond, it becomes alkyne. And the little pattern here is if we go A to E to Y, 1, 2, 3, it's going in ABC order. And so that's kind of a little small helpful way to remember it. But this whole thing, this R and H means, okay, we could have a double bond here where we have carbon things at every little point on the double bond. Or we could have a double bond that's like at the end and has 1, 2, 3 hydrogens. It doesn't matter. We could have carbon things or hydrogen things. They're still alkenes. Does that make sense? Work. Okay. The other thing that's in this hydrocarbon field is an array. So generally speaking, if it looks like a ring and it has some double bonds and there's some resonance going on, call it an array. It's very specifically something called an aromatic compound, but we haven't taught you what that is. So typically think just ring and double bonds and probably resonance, and that's called an array. Yeah. No, there could be tons of stuff. This is, I mean, if you have a main molecule and you have this dangling off of it, this dangly bit is called the array. Yes. So that's kind of the hydrocarbon family. Yeah. So it specifically has to have double bonds on everything in the ring. So you can have smaller arene rings, but like you could also have bigger ones. So you could have one that's like this, where it's like bum, 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 bum. That's an arene ring as well. Cool. Then we have the heteroatoms, so the non-carbon hydrogen things. And you will get to know the oxygen mafia. They are all related to each other. They're up to no good. They're very reactive. So our main auction, the kind of grand boss of the mafia, I don't know anything about the mafia, is alcohols. So if you have an OH on something, it's an alcohol. Now, if instead of an H on one side, so if we just did it like this, we're still at an alcohol. But if we replace that H with a carbon thing, some R group, then it becomes an ether. So it's kind of like if we had this, where we have an oxygen kind of in the middle of some carbons, it's an ether. And you can think of, oh, the oxygen's part of the ether, the background. Now, if it is between some carbons, and then those two carbons are connected in this little three-membered ring, she's an epoxide. Epoxides are fun and fresh and very reactive because they're in this tight little ring and they're very stressed about it. They want to have the 109.5-degree bond angle. Instead, they have this like 60-degree bond angle. So they are like explosive. They're a whole thing. But like that is why an epoxide is different from just an ether. Then we have the acetal and hemiacetal. So an acetal is like you take one ether and another ether and connect them at the same carbon here in the middle. So when you have that happen, you form an acetal. Technically, there's also something called a ketal, but we don't want you to know the difference in this class, so you can just call it an acetal. And so two ethers connected to the same one. And then if you replace one of those ethers with an OH, you have kind of like half of an acetal. So you have a hemiacetal. This will probably feel pedantic and like silly and like, why are we asking you to know this? I'll get to that. Don't worry. I'll get to the why in a minute. Alcohol's cooler older cousin is a thiol. So instead of an OH, you have an SH, and SH is like right below on the table. Generally, if you see thio, it is like talking about sulfur. Then we have amines, and this in R/H3, that looks kind of confusing. It's literally just a nitrogen attached to three things is called an amine. So it could be an H2 attached to carbon stuff, or it could be nitrogen with some carbon stuff, and a hydrogen, or it could be nitrogen attached to all carbon stuff. All of these are amines. Then if you have a halogen on something, we call it an alkyl halide. So this is kind of the extended family, the oxygen mafia. Questions on her? Yeah. It's generally speaking, R is anything. So like, let's say there's a problem where you don't want to write the same thing over and over and it's not really involved in anything. You could just say R equals this thing. And that's an abbreviation that you can use. In this context, assume R is some sort of hydrocarbon. It's a methyl or an ethyl or a propyl, something like that. But it does, for this case, it doesn't matter what the R is. It's just something with carbon. Yeah. 9. Well, it's because these are halogens, the halides. Yeah. Yeah. And it's attached to like a hydrocarbon, so alkyl halide. Yeah. Acetal, hemiacetal. It's not an actual 90-degree. This is the whole dash and wedge, but it's essentially like here, if you did not have this, you would just have an ether. Are you with me on that? And then here, if you have two ethers and they're connected at the same carbon, that makes an acetal. Yes. And then if you have an ether and an alcohol at the same carbon, it's the hemiacetal. Okay, last family are the carbonyl compounds, also called the carboxylic acid derivatives, or CADs. But anyway, the main central kind of word here is carbonyl. So carbonyl is an umbrella term. So if you see a functional group thing on the exam and you write carbonyl, you will not get points because she is not specific enough. Like, she tells you generally that there's a CO double bond, but what is on the either side of her gives you the specific flavor. So if you have on either side of the carbonyl carbons, so like if it's in a chain and you put it right here, then we say it's a ketone. Then if you instead have one of them as a hydrogen and the other one could be a hydrogen or it could be a carbon, It's always going to be on the end of a molecule because you have a hydrogen here. And so in other words, it can't aldehyde. Mm, mm. Now, I know it's awful. This, a lot of people want to look at it and be like, well, we have a carbonyl, then we have an alcohol. So it's two functional groups, carbonyl, alcohol. No, no, no. What do you know about this oxygen relative to this pi bond? What's going to be going on there? Resonance, the answer to everything in organic chemistry. So because there's this resonance here, these three atoms react as one thing. And so they are a functional group all into themselves. So if you call this a carbonyl or a ketone or something, and an alcohol, that is just wrong. This is a carboxylic acid. Now, I tried to set this up in like a smart way of like, if you have a carbonyl plus an alcohol, it's a carboxylic acid. If you have a carbonyl plus an ether, because this is oxygen R group and this is a carbon, so like another R, then it becomes an ester. If you have a carbonyl and an amine on the side, then it becomes an amide. It's just talking about like each of these, there's still resonance. And so they're going to react as their own separate things rather than two functional groups. The last one is acid chloride. We mostly see it with chloride. It technically could happen with bromine. It does not happen with F. So we just have to memorize acid chloride. It's a carbonyl that has a chlorine neighbor. And there is a resonance structure. It's just horrible. So questions about these carbonyl compounds as being a carbonyl plus something else, and it reacts as one distinct unit. Yeah. Like, so that would be an acid fluoride, and acid fluorides don't really form. Yeah. And so the one that you're going to see most often is acid chloride. So we just say acid chloride instead of acid halide. Last one over here that's kind of rando is a nitrile, a CN triple bond. She exists. Now, this diagram, you're not going to be explicitly tested on this, but it's helpful to know. So like this compound right here has resonance, right? This double bond here with this double bond CO. And so this thing reacts as one distinct unit. It's partially an alkene and partially a ketone, so it's called an enone. And it's its own distinct functional group. And so what I want to kind of get across with this is the idea that these compound functional groups exist, and giving them names will be helpful as we go forward. So like in lecture 3, you're going to learn some reactions for enones that do not happen for just ketones. And so knowing that distinction, I think, is helpful for y'all to give you some language to talk about what we're going to learn about. Similarly, if you have an alkene alcohol, it's an enol. But the only reason that these are compound functional groups and their own separate thing is because there's resonance for each of these, like here and here. Over here, these compounds, these are just completely distinct functional groups because there's an sp3 hybrid carbon. Sorry, sp3 hybrid has carbon separating them. So this just reacts as an alcohol here, and this just reacts as an alkene. This is just an alkene. This is just a ketone. Whereas this is an enone and this is an enol. They react differently. That's kind of the take-home message. Yes. Alex?
Yeah, I know.
Yeah.
Is the nitrogen could be bonded to something? Could the nitrogen be bonded to carbon? Or
For an amine?
no, for a nitrogen.
Oh, nitrile, it's specifically to a carbon.
But then could it be also bonded to another carbon on the other side?
So if it did, it would have a positive charge, and that just doesn't really happen normally. But hypothetically, sure. Yeah. So y'all have just like dumped information on you. Where you're really gonna get kind of put to the limit is you're gonna be given a big molecule and you have to identify the functional groups. So take a couple minutes, talk with friends, work through them, try to circle and like identify each of these functional groups, and then we'll talk about ones that come up that are tricky. And if you're struggling on where to start, I would say find an element that's not carbon and be like, oh, okay, this is one of the auction ones. Let me look at the auction mafia. See what's going on. Okay. I mean, it could be attached to like four things, but then the nitrogen's positively charged, and you'll just see that black. So it's technically an ammonium. But like, again, yes, generally speaking, for the exam. Such. The one exception is if it's a neighbor to a carbonyl, and then it say. I make noises. I do like little screams. Amid. There you go. It gets amidst amid. Amidst what? I don't know. Just one more minute here. Katie, I am Alex. Your name is not also Alex. Kirkletter? Alexander. No. Anthony. Anthony. What? Okay. Now you can look at the screen. Wow. How'd you do? Take a minute, check your answers, and then if there are ones that you don't understand, ask about it. Jobel? It's because for an amide, it has to be right here. Like here, it's separated by this carbon, which is sp3 hybridized. So you can't do resonance through that. Like if you tried to push electrons here, this has a hydrogen here, so that carbon has a full octet and all sigma bonds, so you can't do resonance through it.
You know that, oh, wait, that the article on the second
second one, bottom left, this?
Yeah.
Oh yeah, I didn't write the word. Yes. Anthony.
Where it says, sir, moves fast. Why would it start off the?
Because it's an ether, but it's next to a carbonyl. So this has resonance. And so it reacts as one thing with the carbonyl. So I like to think of like, first do the oxygen mafia, and then ask yourself, is there a carbonyl? And if it is, you have to jump to the other family. Other questions on this? Please ask, because if you missed it and you're wondering, other people are also missing it and wondering. We're suffering in silence. Yes. Yes, and by at the end of the molecule, like there's a hydrogen instead of another carbon. Because if there's a carbon, it wouldn't be on the end. There are a lot of them. Again, these are great like flashcard things. And then practicing on the active and the skill builders. But you are fully going to have probably a third of a page on an exam. It's just going to be, we give you a molecule like this, say circle all the functional groups. So if you got that, you got at least 10 points on the exam. Ooh. Wow. Yes, Alex.
What is the like, if the stick, like the circular shape,
It's just showing, so
that shape exists.
So everything here exists like in 3D, but this is a specific one where it's a carbon attached to 4 different things, and we have to treat those a little bit more carefully. That's the subject of all of lecture 4. So, yes. Okay, now bear with me for 2 minutes because I said section I would not teach you anything new, and this is something new, but it's not going to be explicitly tested. I'm introducing it to you to give you a better vocabulary and language for talking about molecules. And I think that this will be a helpful tool for you going forward. At some point, it will be mentioned in lectures, but just like how we did a little FMO or like molecular orbital theory on Wednesday, that hopefully helped you a little bit for lecture 2. I want to introduce this now here explicitly with functional groups so that it will help you with recognizing molecules going forward. Okay, 2 minutes. So we can classify a carbon by how many other carbons it's connected to. So like all of these blue carbons are connected to one other carbon. And so we say these blue carbons are primary carbons, and we indicate it with a 1 and a like little degree sign. Now, secondary carbon, and I will say there's a mistake. I made 2 mistakes so far this semester. This should be a red one. This should be a tertiary carbon. But this one right here, this carbon is connected to 2 other carbons. So it is a secondary carbon. This one, which I corrected here, this carbon is connected to 1, 2, 3 carbons. So it's a tertiary carbon. And we also have quark, same kind of pattern. So it just gives us language to say some carbons are more connected and some are less. And that's going to be helpful later, but for right now, take our word. We can also describe alcohols and alkyl halides with this kind of classification system. So if an alcohol is connected to a primary carbon, one that's only connected to 1 other carbon, then it's a primary alcohol. And so then you have secondary alcohols connected to a secondary carbon. There are going to be some reactions that only happen with secondary alcohols, some that only happen with primary alcohols. So if you have the language, it's helpful. Same thing for alkyl halides. Again, we're not explicitly testing you on it, so I'm going quick. The one that's weird is amines. So amine, you might think, okay, this nitrogen is attached to this carbon. This carbon is attached to 1 other carbon, so it's a primary carbon. This should be a primary amine. That's not how it works. For amines, it's about how many carbons are connected to the nitrogen. So here, this nitrogen has 1 carbon thing on it, so it's primary. This one has 2, so it's secondary. And this one has 3, so it's tertiary. I know that the why of this does not make sense, and you just heard this. Does this make sense? Like if I were to say, what type of alcohol is this? Primary, secondary, or tertiary? You would say 1, 2, 3. Secondary, because this is carbon is connected to 2 other carbons. So it's a secondary carbon, secondary alcohol. And then for this amine right here, you would say because this nitrogen is connected to 1 thing, it's a 1, 2, 3 primary amine. Because amines, it's about how many things are connected to the nitrogen. So that's the weird. You want to try one more time with another amine? This amine right here, this nitrogen. It's connected to two things. So 1, 2, 3. There we go. Work. Beautiful. Again, it'll be helpful later. Now, why do we do all this? Why am I asking you to memorize all this? Why is this going to be such a critical thing? So let's say I'm teaching you reactions. Hi, I'm teaching you reaction. Reactions. Blah, blah, blah. If I said, hey, learn all these reactions, and I presented like a list of like 50 more of these that kind of look similar, that's a lot of distinct information. And that's like a lot of work. Whereas if you notice on these reactions, all of these reactions take, what functional group is this? Carboxylic acid. What functional group is this? And what functional group is this? Ester. Yeah. So basically, these functional groups allow us to kind of tag molecules and say, instead of learning these as 1, 2, 3, up to like thousands separate reactions, we can say this is one general reaction of a carboxylic acid and an alcohol make an ester. That is why it's useful. If you learn these now, like memorize them this weekend, you're going to save yourself a lot of legwork going forward. And that's why we explicitly test this and make you. Functional groups, what they are and why they're important. Does that make sense? Great. I'm going to move on. Okay. MO theory. This was probably where people started being like, huh, you said wave function? Nodes? What are we doing? What are we doing here? So we're not going to be testing you explicitly on that. But this idea of like bonding, antibonding orbitals, and building MO diagrams is going to be fundamental to everything we do going forward. So it's going to be a big chunk of today. It's not going to be all. We're still going to touch on acidity because Tim did sprint through acidity. But MO theory is kind of what takes us to atoms and hybridization, from there to how molecules are reacting. There are two key ideas that you need to know from the MO theory, which is like stuffy. First one, the number of atomic orbitals equals the number of molecular orbitals. So let's remind ourselves of atomic orbitals. So if you're a hydrogen, you only have one atomic orbital, right? You just have the 1s orbital. Then if you are another atom on the second row below, you're going to have an s orbital and 3 p orbitals. And you might have some others, you might have like d orbitals, whatever. Just assume you have the s and 3 p's. So with this, of like everything else has 4, hydrogens have 1, we can count the number of atomic orbitals if we're given a formula. So for example, this molecule, C3H7O, we have 7 hydrogens, each giving 1 orbital. And then we have 1, 2, 3, 4 other atoms, each giving us how many orbitals? Each one gives us 4. So each of these carbons and this oxygen, each one's going to give you 4. So you're going to have 16 orbitals plus 7 orbitals. In total, you're going to have 23 atomic orbitals, which means that you have 23 molecular orbitals. Now, do you remember the process in lecture where y'all were building an MO diagram? And I think it was pretty common for people to be like checking their answer and they're like, oh, I completely forgot about that non-bonding orbital. Or, oh my God, I didn't do any antibonding orbitals. Like, it's hard when you're trying to do the MO diagram to know that you've gotten them all. And this is the thing that tells you how many you need to find. So if you calculate the number of atomic orbitals because the number of AOs equal the number of MOs, then this says, okay, in this molecule, when I'm trying to do the full MO diagram, I need to identify 23 molecular orbitals of like bonding, antibonding, lone pair. It gives you a kind of like, it lets you know if you're done, essentially. Second key idea, for every bonding orbital, there's an antibonding. So has anyone done any like physics, even like in high school, and talked about waves? Has anyone heard about waves before? Waves. So do you remember hearing like there's like a positive phase and a negative phase of a wave? And then you also might have talked about combining waves. So if you combine 2 of the same phases together, then it's going to get bigger and you'll have a bigger positive, bigger minus. Does that kind of ring a bell? I think it was called like interference. I don't claim to know physics. And then if you had kind of like a positive negative and a negative positive, and you try to combine these, then it would just cancel out. this idea kind of familiar. The canceling out is like the anti-bonding orbital, and then the getting bigger is like the bonding orbital. So bonding molecular orbitals are the in-phase overlap of these atomic orbitals. And this is the whole thing that's like crazy and like Schrodinger or whatever. Electrons are particle-like and wave. They have phase, but they also have position. That's a bit too much. Just know you can overlap in phase or out of phase, like a little plus plus or the plus minus canceling out. Now, an antibonding orbital, generally speaking, is going to be empty. Because if you put electrons into an antibonding orbital, it breaks. Can we say that as a group? If you put electrons into an antibonding orbital, it breaks. It's that easy. Last two things. So sigma bonds, remember they can be between any two of these. You could have like an sp and an s, or you could have an sp2 and an sp overlapping, and that makes a sigma bond. sp3 and sp3, any of those work. But pi bonds are only between p orbitals. So one thing that you're gonna have to do on the problem set, and we might ask you to do on like an exam or something, is to draw molecular orbitals, to do a little sketch of what they look like. So I've provided a lot of these for you. And see over here, this would be like a carbon, carbon, both of these sp3. And if we put the shaded regions so that they overlap, and we put the empty little nubs on the other side, this is the in phase overlap because the shade goes on the shade. And so this is our bonding. Whereas if we had like an unfilled and a filled bit here, that's out of phase being put together. So you have the anti-bonding orbital. Do these pictures make sense? And do you think that you could draw them on the problem set this weekend? I see a little bit of concern, but general nod, so I'm going to keep talking. The last thing is electronegativity affects these orbitals. So in a CC bond, what's the difference in electronegativity between carbon and carbon? 0. But in a carbon-oxygen bond, which is more electronegative, work. So in a bonding interaction, you are going to put the electrons closer to the more electronegative atom. So whereas the CC bond's just kind of like this even like little lump, the CO bonding interaction is going to be kind of like this lopsided lump, where you're going to have more electron density around the oxygen and a little bit less around the carbon because the oxygen is greedy and more electronegative. I shouldn't shade both of them. One should be unshaded. So bonding orbitals have larger lobes on the more electronegative atom. And because of like quantum mechanics and symmetry or some nonsense, anti-bonding orbitals have larger lobes on the less electronegative atom. So what that means is here is a normal anti-bonding orbital where you have the two p's, but they're out of phase and they're kind of like repelling each other, or they look like they're kind of wedged away. What you're going to have over here is you're going to have big nubs on the carbon and small nubs on the oxygen, because you have larger lobes on the less electronegative atom for antibonding orbital. So let's say you are a nucleophile and you want to attack a carbonyl. So you're a nucleophile, you have electrons, you want to attack this carbonyl. You could hypothetically attack the carbon or the oxygen. But either way, when you're doing the attack, where are you putting the electrons? Into what orbital? Antibonding orbital. You need some empty orbital to put electrons into. And the only empty orbitals really on molecules would be like an empty non-bonding orbital or an antibonding orbital. Okay, so if we need to put electrons into our antibonding orbital, is it going to be easier to attack the carbon side or the oxygen side? Carbon, because it's literally like, think about you're playing soccer, you have a bigger goal to hit. And so it's going to attack the carbon rather than attacking the oxygen. And we're putting electrons into the antibonding orbital for the pi CO. And we know that when we put electrons into an antibonding orbital, what happens? It breaks the bond. So we break that bond and push the electrons up to the oxygen. I know that that's like a bit much, and this is something that you're going to do explicitly in lecture 3. Does that kind of idea and process make a bit more sense? Work. Then, yes.
When you put in the antibody, are you also putting along So that it's so much not-
You're just kind of shifting. Like the carbon's going from having these two electrons filling its octet over here to now you're creating a new bond with a nucleophile that replaces that bond.
Okay.
So it's going to have a full octet the whole time. Now, I like to think of the like ranking energies and things like you have like little energy buckets, and the buckets are symmetric. So the lowest energy bucket is the sigma, the highest energy bucket is the sigma star, and you have pi, pi star, and then non-bonding atomic orbitals in the middle. This is an order that you just need to memorize, but it should be pretty quick because it's not that detailed. 1 second. But then within each of these buckets, the thing that determines what's higher or lower in energy is this low energy trifecta. So things more electronegative, more S character, more positive formal charge are going to be lower in energy. So here you have sigma CO lower in energy than sigma CC because O is more electronegative. And then same hydrogen is the highest of these sigmas because it's least electronegative. But the sigma CO is the lowest energy overall. But what is the highest energy overall? You can see I wrote it out. Sigma CH. So it's not going to be a completely symmetric drawing. Like your lowest energy one down here is not going to be the same as your highest energy over here. It's within these buckets, the lower energy trifecta rules. So of the sigma stars, sigma star CO is lower. And just like for the sigma, sigma CO is lower. Does that small distinction make sense? Like grading exams, grading the MO question on exams, because you're going to have a question that's just exactly like this. Or really, it's kind of like this page where we're going to give you two molecules, say build the MO diagram, identify the homolumo, predict how they're going to react. That's a page of your exam right there. And easy points that students miss each year are they really make it a fully symmetric diagram. And that's just not the case with these. Questions? I see confusion.
Yeah, I just question, so you can more of it.
Yes, I would say the buckets are symmetric, and then within the bucket, it's a copy paste. Yes. Yeah, shout out. So a sigma and O. That's a great question. What you do is you add the electronegativities. So think about it this way. Nitrogen and oxygen are both fairly electronegative. So this is going to be even lower than sigma CO because it has two of those more electronegative atoms, whereas this just has one more electronegative atom. Yes, again, take the electronegativities of the two elements and add them together. And whichever one's the biggest, it has the most electronegativity overall, is going to be lowest. So OO is going to be large, more negative. OF is going to be lower than that. FF is going to be lower than that. Yes, good. Okay, now I'm going to do this one really quick with y'all to just go beat by beat how you build an MO diagram. I'm going to have you do it on your own in like a couple minutes. So I list out the instructions like step 1, 2, 3, 4, 5 explicitly. First thing's drawing the Lewis structure. We have H, H, C, O. We make the single bonds first. Our valence electrons is 4 plus 6 plus 2 equals 12. I know I'm going fast. We have 2, 4, 6 electrons already here. We do 8, 10, 12. Then that's a minus and that's a plus. So to try to minimize formal charges, we'll make a double bond here. And now we have all the valence electrons, we have our Lewis structure. That's where y'all are going to need to be closer to the exam. I will say, we're not going to really ask you to do a lot of Lewis structures from scratch. Most things will give you the formula, like we'll give you the structure, not just like a chemical formula. But again, this becoming more of a background skill rather than the main event, I think is the big thing to emphasize. So we've done steps 1 and 2. Count the number of atomic orbitals to get the number of molecular orbitals. Well, so we have 2 hydrogens. So how many orbitals do we get from the hydrogens? 2 total. So 2 times 1. And then we have 1 carbon, 1 oxygen. How many orbitals do we get from each of those? 4. So we have 2 times 4. So you have 2 plus 8, we have 10 AOs. So that means that we have 10 molecular orbitals that we have to identify. So name a bond, any bond. I heard sigma CH, and we have 2 of those. Sigma CO. Pi CO. 2 and O, good. And then we're at 2, 3, 4, 5. Oh, wait, we have 2 of these, 6. So we're still missing 4. And that's how that number 10 can help us out. What are the 4 that we're missing? There we go. So we have 2 sigma star CH. We have a sigma star CO. We have a pi star CO. And then there's no antibonding orbital for non-bonding. Non-bonding is just kind of non-bonding. Okay. Now I'm gonna make my little energy axis, and then I'm gonna start and rank them bucket by bucket. So what's the lowest bucket energy-wise? The lowest bucket type of bond. Sigma. So we have sigma CH, sigma CO, which is gonna be lower. Why? Electronegativity, good. Then we have the 2 sigma CHs, which are the same energy level. Then what's the next bucket? Pi, and so we only have 1, the pi CO. Then what's the next bucket? Non-bonding, we have the 2 lone pairs on option. What's the next bucket? Pi star, we only have 1, so it's the pi star CO. Top bucket. Sigma. So we have sigma CH, or sorry, sigma star CH and sigma star CO, which is lower in energy. The CO, so it's not totally symmetric. Yeah, the sigma star CO is lower in energy than the sigma star CH. Cool. We've done this, this, this. Last thing, we take our valence electron count and we populate this with electrons. So we have 12 electrons. We start from the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what we see is all of our bonding orbitals and our non-bonding orbitals are filled. And that's kind of what we would expect. If you are doing this MO diagram and you are putting electrons into an antibonding orbital, typically something has gone wrong. You also could have your non-bonding orbital be empty. So you could have an empty like p orbital on a carbon if you had a carbocation. But this is kind of the process. So you're going to get a chance to practice this in a minute and put it together with some other stuff. But any questions on this before we talk about frontier molecular orbitals? Yeah. Like it's like a quantum mechanics math thing, and like I don't really care about it. No, I'm just being honest, man. I don't want to like BS you. Yeah. You first do it by bucket, and then once you're in the bucket, then you do low energy trifecta. So like, for example, we said the lowest bucket sigma, and then between the sigma CH and sigma CO, the CO is lower energy because of the lower energy trifecta. And then once we got to the sigma star bucket, we said that's the highest bucket. And then the sigma star CO is lower energy because it's more electronegative. Yep. That would be sigma and H because nitrogen's more electronegative than C. So it's going to be right here. Sometimes, but rare. Yep. Yep. So let's say you had a carbon-carbon bond that was sp hybridized versus a carbon-carbon bond that was sp2 hybridized. Like let's say you had a molecule that was like this and this. So you're going to have a sigma cc over here where they're both sp2, and you're going to have a sigma c over here where it's sp. But we're probably not going to give you that. So that's the only time it would really be the tiebreaker. It's really mostly electronegativity. I'm going to move on. So not all the molecular orbitals are created equal. There are 2 we care about more than the rest. and they are at the frontier of reactivity. So they are either the highest occupied or highest filled molecular orbital, called the HOMO, or they are the lowest unoccupied molecular orbital, the LUMO. And especially as a queer chemist, I really want to emphasize that you need to be able to spot a HOMO and a LUMO. You know? So why do we care about these? The energy levels of your HOMO and LUMO are going to come together and create a bonding interaction. And if you have a HOMO and LUMO closer in energy, what you're going to get is more stabilization. Whereas if your HOMO and LUMO are different in energy, you're going to get less stabilization. So kind of like, I know that this is a weird diagram. Do you see how when we started off similar, we dropped energy for the bonding interaction a lot more than here? These started off at different energy levels and dropped less. That's kind of the idea. We're not going to ask you to draw a picture of that, but that is like the HOMO and LUMO being closer in energy makes it more stabilizing when that bond happens. Cool. So HOMO and LUMO are a specific orbital, and it depends on the molecule, and it's from the MO diagram. But if we generalize it a bit, a HOMO is an example of a donor orbital, something that can donate electrons. And typically, there are two types of donors that we consider especially good. So one is a lone pair, except for in halides. So why would lone pairs on halides not be good donors? Yeah. Yeah, they don't want to share. They don't want to donate. They said, I have my electrons, get yours. And then the other good donor are alkenes. And it's really just because it's like you have a lot of electron density built up between these two atoms because you have 4 electrons there rather than just 2. And so it's going to be more willing to donate. It's also pi bonds are higher in energy than sigma bonds. So they're going to be higher energy donors. They're going to be better donors. Meanwhile, acceptors, remember the LUMO is a specific type of example of an acceptor, but generally good acceptors include empty orbitals, typically found on a carbon or a boron, pi star orbitals, except for pi star CC, and then sigma star CX orbitals. Now, why do you think sigma or pi star CC is not a good acceptor? I know Tim gave kind of hand-wavy answer, but I think that there's an answer that y'all can latch on to. Let's look at the pi star CC versus the pi star CO. Why would the pi star CC not be as good of an acceptor? Anyone? Yes, or think about like it's an empty orbital for the antibonding. The target's bigger for CO, whereas the target's smaller for CC. And so it's kind of like a space argument that a pi star CC is not a good acceptor because the goal is smaller, the orbital is smaller. And then a sigma star CX is also going to be a good acceptor because an X, where X is an electronegative element, it's going to be the lower in energy of those sigma stars. And remember, we want low energy LUMOs and high energy HOMOs to come together to try to be closer in energy. And the closer they are, the more stabilization. Cool. So specific orbitals, generally they're these types of orbitals. And the molecule that donates in a reaction, the molecule that the HOMO does something and donates electrons, we call that whole molecule the nucleophile. And the molecule that accepts electrons in a reaction, we call that whole molecule the electrophile. So HOMO, LUMO are just specific bonds. They're types of bonds that are donors or acceptors, and they're on molecules called nucleophiles and electrophiles. Now, a specific type of nucleophile is a base. A base is a nucleophile that donates electrons and in return gets a proton. An acid is an electrophile that accepts electrons and in return gives up a proton. Those definitions of acid-base things might feel a little bit weird at first. I think the general thing to know is base is a type of nucleophile, acid is a type of electrophile. So I made a little summary. So in a reaction, you would have the HOMO, which is a donor on the nucleophile, which could be a base. The electrons are going to flow from that donor orbital on the HOMO to the acceptor orbital, which is a LUMO. And the molecule that has the LUMO, that's the acceptor, is the electrophile, which may or may not be an acid. I know, terminology is so fun. Questions on this? Okay. So what I want you to do is I want you to start here on this problem. This is page 11 of the problem set, where you're going to be building MO diagrams for two molecules and then trying to predict the reactivity. I don't expect you to be able to do two of them in the time I'm going to give you. So try getting one MO diagram on your own or talking with friends. And then we're going to talk through kind of the second part of the reaction together. If you finish your MO diagram early, you can either try doing the other MO diagram, or you can try working on these page 15 arrows. And depending on like how people feel, we'll go over all of them or just parts of them. So we're working page 11 and page 15, the last three examples in the problem set. And I will circulate and answer questions. Mara. That's your name. No. What's your name? Tate. And the other Tate did not show up. Work letter. forget about, did you get both of them here? Did you do both of the NA? So fun. Not the full numbers, but the trend. I think the hardest one here is the CL versus the O. And just knowing that the auction's the second most electronegative element is the way that I would do it. So I know people aren't fully done, but let's talk about some things. So did you get for A that the HOMO is going to be the lone pair on the nitrogen and the LUMO is the sigma star NO? Cool. And for B, if you did it, then you can check it. If not, just take my word. The HOMO is going to be the lone pair on the Cl, and LUMO is going to be the pi star Cl. So now we are going to try to predict how these two molecules will interact with each other. And that's kind of like this, ooh, we're doing some experimental, some creativity. We're trying to put this together. So the way that we do it is we look at both of the HOMOs and we say, which of these is a better donor? A lone pair on nitrogen or a lone pair on chlorine? Nitrogen, why? So this is the better donor. And then I guess the chlorine comes second place as the donor. And then which of these is a better acceptor? A sigma star, or a pi star, Cl? Why? Lower in energy. So what we see is we have one that's the better donor and the other one that's the better acceptor. Oh my gosh, I'm having a brain fart. Is it ACCEPTOR? Okay. I was like, OR, ER. So what's going to happen in this reaction is we expect this better donor, the lone pair on the nitrogen, to donate into the better acceptor, the pi star Cl. So let's track this. So draw the lone pair on the nitrogen. That's our donor orbital, right? Then we're going to start a curved arrow over here. And then this arrow can either attack the sigma or the pi star CO at the carbon or at the oxygen. Where is it going to attack? Carbon. Why? Because it's a bigger target. Carbon's less electronegative. So we are going to attack this carbon. So that is what we expect the HOMO-LUMO interaction to be as the two molecules interact with each other. But this carbon already has 4 bonds. So something needs to break. And as we all know, when we put electrons into an antibonding orbital, the bond, wow, quick studies. So we are going to break that pi bond and put the electrons just up on the oxygen. So what our product's going to be is we draw what the molecules were, and we should reflect the changes that our bonds made, or sorry, that our arrows made. So you're still going to have a single bond up here to the oxygen, but now the oxygen's going to have a negative charge because you push electrons up. And then this carbon, you created a bond between this nitrogen when it attacked this carbon over here. So you have this nitrogen right here. You still have the H2, and then you have the OH. But now this nitrogen's attached to 4 things. So what's its formal charge? Positive. Questions? Yeah. Lowest and unoccupied. And then when you're trying to figure out which of them is going to be the overall acceptor for a reaction, you look at both of their LUMOs and say which one's the better acceptor orbital. Well, it's the pi star because that's lower in energy. Really? It's not about difference. It's about sum. Yeah. So like N and O total, their sum of electron negativities is lower or is greater than the sum of electron negativities between O and H. Yeah. Jonathan. Are you talking about like between the lone pair on the nitrogen and oxygen
Oh,
and chlorine? So, I mean, generally speaking, the criterion that we use to grade it is like what is a good donor over here. So like in this case, it is the case where we're choosing between a lone pair of nitrogen and lone pair and chlorine. And it's not that the lone pair and chlorine could never attack. It could, but this is a much better donor. And so that's going to be like we grade them using these kind of criteria that we just say these are good, these are bad. It doesn't super matter, but the thing is, when we talk about reactions, we move from just energy to also like kinetics and orbital size. And because these electrons are being held kind of further away from the atom, or sorry, because these electrons are more concentrated, because this is the second row, this is the third row, this more concentrated lone pair is going to be better to donate because you have more electrons in a smaller space. Yeah. I'm gonna kind of skip this because you have the skill builder page and everything, you have the answers for her. But this is going to be practiced really with those arrows. So like just very quickly, seeing, okay, let's map these molecules onto each other. H3O plus probably turned into H2O. So something needs to take a hydrogen. And then over here, we added a hydrogen on this oxygen. So this oxygen, it's probably the donor going to be a lone pair because that's a donor that's on the oxygen. And it's going to grab the hydrogen. But then we need to do something with the electrons. We need to put those electrons back on the oxygen. So here, this oxygen has 2 lone pairs, but here it only has 1. The second lone pair came from that bond. Making sure that these arrows reflect changes in the atoms and in the molecules is the important skill that you're going to be developing here. And if you find yourself drawing arrows that are backwards, that's a big red flag. So we'll want to correct that soon. That being said, I'm going to talk about acidity now. Is that okay? Cool. Work. So acidity is one of these concepts, again, that you've heard in Gen Chem, and we're going to kind of like tell you what's important about it for organic chemistry. So Hendelson Hasselbalch, I don't know her. Ka, who is she? PKB. pKa. That's the only one you really need to know to measure acid strength for organic chemistry. And you need to know lower pKa is a stronger acid. So when we say it's a stronger acid, we should ask what that really means. So a strong acid is an acid that's reactive. It really wants to give up its hydrogen. And when we say that something is a weak base, like a weak conjugate base, we're really saying that, oh, that base is stable. That's what we mean when we say weak. And so what makes a molecule stable would be like not having charges, or if you did have a charge, a negative charge, putting on the more electronegative atom. So we're going to be thinking about these ideas of stability and reactivity as kind of like very, very closely related for acid and base. And the central idea that you probably heard in some class that I'm going to state in this like short little acronym is strong acids have weak conjugate bases. So those acids that are really strong and want to react are going to have very stable conjugate bases. So we can use the stability of a conjugate base as a way to kind of grade and rank acid strength. And so we're going to do a little face off. And this is where I have to admit the second mistake that I made of the semester. So do you see how this Y says resonance delocalized and greatly stabilized, whatever. And this Y is the same. And this Y is the same. It might have been because someone copied and pasted. So can you just cross out these two? The reasoning is not right, and I will fix it later. But someone called me out on it, and I was like, I really just wanted to be done with this page because this page alone probably took like 4 hours. There's a software called ChemDraw, and then I use like Google Slides and PowerPoint to kind of lay things out. Yeah, one thing I will let y'all know, I would say I spend as much time on this course as y'all do. Yes. I might. but work. So the factors affecting acidity, we're using this like trendy buzzword careo to organize it, which I'm like, that's very like pre-medi, is very like, it claims to be charge is most important, then atom, then resonance, but it really depends, and I think it's kind of BS, but to organize it, pre-meds love the acronym, so here we go, careo. So what we're going to do for each one of these is in the face-off, we're going to first draw the conjugate base. Do you all know how we draw the conjugate base? Take away a hydrogen. So here, the conjugate base, we have NH2, and we have NH that has a negative charge. After we draw the conjugate bases, we ask which of these conjugate bases is more stable? And the left or the right? The left, why? No formal charge. So this is the more stable conjugate base. It's the weaker conjugate base. So its conjugate acid is the stronger acid. So ding, 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 our winner is NH3 plus. And so that is charge. The more positive formal charge is the more acidic. And the process that we did is kind of explaining it with the conjugate bases. But if you just see positive formal charge, you can circle that. Joel. I don't think about it that way. I think about it as like, this base is weak because it's stable. This is fine existing just how it is. Whereas this nitrogen has some beef with people. It has a negative charge. It really wants a partner to come along and share these electrons so it doesn't have to have all these dang electrons going around. This thing does not want to just exist on its own. This thing does want to exist on its own. Is that? Because if you're stable, are you going to want to like go out and react with other people? No, you're going to want to stay in and watch Netflix. So this is like the working the boring 9-to-5 job. And this is like, I'm gonna go out to the club and do something. I don't know. I don't go to a club. Okay. So next one, let's draw the conjugate bases of each. So we have NH minus versus O minus. Which of these is going to be more stable, left or right? I'll ask again. Which is going to be more stable for these conjugate bases, left or right? Right. Why? More electronegative. Good. This one's more stable, so the OH is the better acid. Next one. Drawing the conjugate bases, O minus and S minus. I'll give you a chance to catch up. Now, which conjugate base is more stable, left or right? It's right. The reasoning here is negative charge. When you have an s orbital, so like imagine the sphere is like the 2s orbital. It's kind of this size. And imagine this sphere is like the 3s orbital. It's this big. If you can spread out the negative orbital or work, if you can spread out the negative charge in this big space or this small space, which do you think is going to be more stable? The big space, because you're spreading out the negative charge over more like actual 3D space. And so sulfur, because it's further down on the periodic table, has a larger radius. You're spreading out that negative charge among a larger space. And so this one's more stable, which means the SH is a stronger acid. Yes, Tate. Taft. Wait. Tate. John. Work. Hi. This is, I'm gonna get to that. I'll get to that. Let's keep doing these last ones really quick, and then we'll do some problems and something more interactive. So we're removing the hydrogens, and then between these two conjugate bases, left and right, which is more stable? Left. Why? It has resonance, so we're spreading out this negative charge among 3 atoms. So we have a resonance structure where the negative charge is over here. And so this is the more stable conjugate base, which means it has the stronger acid. Okay, next one, O minus. And then we have the O minus, but we have 2 Fs. Now, before I just ask you, I like to think about induction as Induction is kind of like tugging on the electrons, but not sharing. So like, imagine if you are doing resonance, you are a person with a negative. You are dealing with a problem and you're sharing that negative with your ride or dies. And they're like, you have a problem, I have a problem. We're in this together. Where induction is different. Induction is like having a friend who likes to hear you complain. So if I'm the auction over here and I'm negative, and I want to talk about why I'm kind of negative, these friends are like, oh yeah, tell me more. I want to hear all the complaints. And so it doesn't help as much as ride or dies that are taking on the burden with you, but it feels better than being alone with a negative. Does that kind of metaphor make sense as to what induction is kind of doing? Work. So if we have a negative charge and we can complain about it versus a negative charge and we're alone, which one's going to be more stable? Complaining. More stable. So this is the stronger acid. And then if those friends that we want to complain to are closer versus the friends being farther away, we have to travel to complain. No, I want to complain right where I am. This is going to be the stronger acid when they're closer or when you have more of them. Last one. So we have a negative charge over here on the carbon and a negative charge over here on the carbon. And what orbital is this negative charge in on the left? sp2. Because remember, the p orbital is doing that pi bond, and so the only other orbitals available on there is sp2. So this negative charge must be in sp2. And then what orbital is this negative charge in? sp. Now an sp orbital is what percent s? 50% s. And then an sp2 orbital is what percent s? 33.3, thank you, percent s. So which one has more s character? The right. But now why does that matter? So the way I like to think about it is s character being stabilized is kind of like if you are doing an s orbital and this is your nucleus, your electrons are always going to be closer to the nucleus than a p orbital, which can get a little bit further away, right? So remember, the nucleus is positively charged and the electrons are negatively charged, and you know opposite charges attract, right? Well, there is actually like an energetic like savings bond that you get, like an energetic favorability that you get from putting plus and minus close to each other. And that's called like an electrostatic interaction. And with an S character or more S character being closer for that positive negative, you're more stabilized than if it's further away. So that's kind of a little justification for why S character matters. But honestly, you're going to be using the S character justification so little that like, meh. So comparing between categories is hard. Specifically, the ones that stand out to me as ones that kind of win things are resonance, atom, and charge. Those are going to be the ones that you see most often. But generally speaking, we won't ask you to compare between categories on Cario unless we are asking you to use these benchmarks. And so I think Tim was really nice about it yesterday, and I'm not going to be nice about it. These are values that you have to memorize and you will need to know on exams. He was like, oh yeah, we kind of want you to know it. No, there are going to be questions that to answer the question, you need to have these two columns memorized. And I just don't want to like be playing games with that. This is giving you context for the acids frame. Because if I told you that the pKa of something is like 20, that doesn't really mean anything to you without context. Like soon you're going to learn how all these molecules react. And then once you have this memorized of like, this is the context of things, then when we encounter a new molecule and we say the pK is -2, you're like, oh crap, this is like hydronium. My gosh, okay. Like it's about kind of introducing you to this system where you just need some sort of backup. The conjugate base is not something you need to memorize because you can just remove a hydrogen. This name stuff, that's kind of functional groups, which you're already memorizing separately. So you don't really need to bother with that. Make a flashcard that has this on the front, this on the back. I would say try to have these like down pat by like next Wednesday. I know that's a lot. We move very fast. I'm sorry. But this is going to help you break ties between the different effects, between the oxygens and the nitrogens and the carbons, where things go. That's a lot. I just threw a lot at you. I'm going to do one last little small thing, and then I'm going to take a little poll. Last little small thing. if we have pKa's, we can connect this to KEQ. So KEQ was the thing that told us whether reaction was like product favored and going forward or backwards. So what values of KEQ meant the reaction was product favored? If it was greater than what? 1. And if it was less than 1, it was reactant favored, right? The backwards reaction. So what we can do with an acid base is use this formula. So we say that the KEQ is 10 to the pK of the product acid minus the pK of the reactant acid. So let's break it down one step at a time. Products. Which of these is an acid? NH4 plus. And then on our chart, we know that the pKa of this is 9. Or we will know based on our chart. Then on the reactants, which one of these is an acid? As a hint, what is the name of this functional group? So if we look up at the chart that we don't have memorized yet because you saw it yesterday, we know that the pK of this is 5. So we know the KQ of this is 10 to the power of the product pK, 9, minus the reactant pK, 5. So this is 10 to the 4th, or 1,000, right? That's 10 to the 4th, or is it 10,000? 10,000, thank you. I'm forgetting how to spell, I'm forgetting math. And so, is this reaction product favored or reactant favored? Product. So it's just a little application of pKa things that's going to be important for organic. Questions on this? I know I throw a lot at y'all. Sections move fast as well as lecture. But the thing is, I'm trying to do this in a like less fluff way and try to get to the point of what you need to know and let you know what's important. I don't expect you to walk away from section being like, I feel so much better about the class. Everything's fine now. But I expect you to have seen some tools and to be better able to approach some things and to know better what's important. That's what my hope is. So now it's time for the poll. So the poll is, we have 2 things that we can do with the last 15 minutes or so, 12 minutes. One is, this is challenge problem 9. This is fully just a PSET question. And we could work through it together. But just before you say, oh yes, I want to do that, I want to do the homework, this is a bit easier. So you look at the 3 things and you try to say what is most acidic. Look at the difference between them. Well, these are all like carbon-carbon bonds. And so this is sp3, this is sp2, this is sp. And we know more S character is more acidic. So C, B, A, Y, S character. That to me is an easier skill. And this challenge problem page, I think that y'all can do on your own fairly well. But if we want to just master that and get it like feeling good, we can do that. The other thing that we can do is we can try working on the extra challenge problems associated with acidity. Now remember, extra challenge problems are exam level problems, and this is going to be much harder and feel uncomfortable. And so this, if you want to do this, it's going to be kind of a group experience where I let you look at it for 4 or 5 minutes on your own. You all are very scared. I maybe give you a couple pieces of advice, and then we talk about how to approach a question like this. Given that, who wants option A of challenge problem 9? Who wants option B of extra challenge? I know I hope that y'all would say that. And maybe I was a little selective with how I explained things. But PDF version of Canvas, we prefer to like get a Canvas, but I think just simulating exams, real paper is nice every once in a while. Okay. Before you jump into it, I want to give you a couple pieces of advice. First piece of advice, read this very carefully. Specifically, this. If you do not account for this, you can't do the problem, or you are going to do the problem incorrectly. That this one piece of information is critical for the whole thing. Part A is the hardest. Part B is easy and part C, I think, is easier. So if you get stuck on part A and can't figure out what to do with this, go on to part B and C and try to get those. So I'm going to give you a few minutes just to work on it on your own, then we'll talk about it. Just one more minute on your own and then we'll start talking. So this instruction material says in the last sentence, deprotonation of A with hydroxide yields water and a monoanion B, which appears pink and in which there is no longer an sp3 hybridized carbon. So in A, where is the sp3 hybridized carbon? The middle. So somehow, whatever we do needs to break a bond here. Now, we know we're going to do a base, and our base is hydroxide, right? And what is the acidic proton that we're going to take? The hydrogen on the OH. And is it clear that these are both equivalent? Like these are the same group, so we could attack either one and it's fine. I'm just going to attack this one arbitrarily. So somehow we need to do stuff that's going to break this bond. So bear with me. When we attack this, we are taking the proton, but these electrons have to go somewhere. So where do you think these electrons should go? So a lot of people do this. And then you have this whole thing where you just have O minus over here, and you still have the sp3 hybridized carbon. So we are not done. So what else could we do with those electrons? You could. You're going to take these electrons and make it into a double bond right here. Okay, but that presents some issues still, right? Because this carbon has 1, 2, 3, 4 bonds already. So which bond are we going to break here to make room for this new bond that we're going to create? The double bond, because pi bonds or anti-bonding orbitals for pi are lower in energy than sigma. Okay, then why don't we try that strategy again? We now need to move these electrons down over here, but then this carbon still has too many electrons, so we break the pi bond again. And now this is where the question gets a little hard. So we've done this, and now we're at this point, and we need to figure out, okay, if we make a bond here, which bond do we break? Do we break this sigma CC, this sigma CC, or do we break this sigma CO? The lower energy LUMO is going to be the sigma star CO. So we are going to make a double bond here. And when we do that, we're going to be putting electrons into the anti-bonding CO sigma. When we put electrons into an anti-bonding orbital, the bond, so we push these electrons onto the oxygen. And what we've done now, if I'm going to kind of draw the skeletal structure of that transformation that we just did. So this is kind of everything that did not change, right? Like the only thing that I've done so far is I've broken that bond. But we need to make all of the changes that our arrows did. So our arrow here made a double bond. So we need to have a double bond between this oxygen and carbon. So this becomes this. Then our arrow here made a double bond right here. So we're going to have a double bond here. And that's from this arrow. Those electrons became this double bond. Then these electrons right here became a double bond right here. And now we have reflected all of the changes that our arrows brought about and this new structure. Now, just to double check, are there any sp3 atoms in the new structure? No. This whole thing happened because of resonance. So if we just had single bonds here and did not have any double bonds, then this wouldn't have happened. We would have just plucked off here and then put down the oxygen. And also, you knowing to do this whole thing, you could not have figured it out unless we told you this. This is the kind of critical point. So right now, this probably feels crazy. This feels like, you're asking me to do that? I can't do that. This, you are going to get more comfortable with doing more arrows. Like right now, this all feels very new. On Wednesday, you're going to start doing reactions, and you're going to have some reactions that have 20 arrows. Like not all in one step, but you're going to be doing a lot of these arrows. The rest of organic chemistry, lecture 3 and then lecture 5 and beyond, are arrows and structures. And so it's a big, important concept to really try to nail down this week. Really quickly, I'm going to talk about B and C. So B says that this thing, A, its pK is 9.5. Use what we know about our memorized pKa values to figure out the KEQ. So remember, it's 10 to the power of the product pKa minus the reactant pKa. So within the products here, which one is going to be the acid? Just the water. Because remember, this was the acid over here. It's made a conjugate base. So this is going to be the acid in the product. And on our little Yossified pKa chart, what's the pKa of H2O? 16. And then they told us the pKa of the acid over here is 9.5. So what's 16 minus 9.5? 6.5. So our KQ is 10 to the 6.5. Is this reaction product favored or reactant favored? Product favored. Great. At the end, I'll answer. Last thing for C really quick. They say, hey, this molecule is similar to this one. What's the difference between them? We've added bromines. Okay, and they want us to figure out what the pK of this is. We don't know pK of this. What are we supposed to do? Well, they told us the pK of this is 9.5. So if they had the exact same pK, it would be 9.5. We can assume if this is more acidic, it's going to be 7. And if it's more basic, it's going to be 12. So how do those bromines affect acidity? Inductive effect. They're the friends who like to hear you complain. They're going to tug on those electrons just a little bit and help stabilize it. So if this is going to be the more stable conjugate base, is this the stronger acid? Yes. So what's the pK out of these three options? 7. So this is what I mean about like, you're going to need to know those pK values that we gave you. You're going to need to know Careo and be able to compare things. And we're going to give it to you in situations that feel weird, that feel kind of new, and you're going to have to apply the information rather than just kind of the simple ranking. This is to build experience. This is like to show that you know what's going on. If you did not feel okay on A, that is fine. I would not expect anyone here to have just gotten A off the bat. I would actually expect, I'd be surprised if you said, oh, I got all that. And if you did, good for you, but that wasn't me. Like, this is the thing of we're learning it now, we're exposing to you to it now, so that when you get a similar thing on an exam, you have something that's similar too. Exam questions are going to be this level of difficulty, but you will have seen these type of difficult problems before. With that, thank you for coming to section. I know I went a couple minutes over. I will see y'all next week. I sent out a Canvas announcement with all the reminders and everything. Email me if you need help, anything like that, and I'll stick around for some questions, okay? Thank y'all. Oh. Hi, Katie. Okay.
So why wouldn't be small specific?
Remember, we're talking about the stability of the conjugate base. So we're saying, hey, this is the conjugate base up top for this one.
Right.
And then we're comparing it to this conjugate base.
Oh, so we were comparing. No.
Yes,
got
yes.
it.
And also I forgot to write this in, but thank you, I appreciate that. The last part? Yes, but do you mind if I wait for the other specific questions? Yeah. That's it. You have a hexagon necklace. That's the hexagon necklace. It's very organic chemistry. So your Newman projections, you know that there are going to be some energetic costs with how the molecule sits. Eclipse is going to have a cost, and Gaussian reactions are going to have costs. So basically what you do is write out all of the staggered conformations, write out all the eclipse one, and for each one, add up the cost of those positions. And those are going to become like little benchmarks, little minima and maxima here on this chart. Yes, yeah. So it basically, I think it's going to say set 0 degrees is the least stable conformer. So if you do that, start at the least stable, then rotate the back one 60 degrees, then that's which one you should put in the 60 degrees. Then rotate the next one 120 degrees from the original, and that's how you get the next one. Does that make more sense? Work. Yeah.
Can you explain how we decide which one is the better donor and acceptor?
It's because we told you which ones are good donors and which ones are good acceptors here. So you use this criteria.
You show from one to down
Mhm.
one. And then,
So, yeah, but
I was gonna ask if the and here.
so this is the thing. It's a balance between me spending time making like really detailed annotated section notes versus making the other section notes. And so I think right now it's going to look like that I need a little bit more time to finish all the section notes because it's taking forever. And so I don't think I'm going to have something fully posted that's going to be like walking through everything. But a lot of them, like these, everything on here is a skill builder, you have the solutions. This is a challenge problem, the solutions are gonna be released after you turn the piece set. This is an extra challenge problem, the solution is gonna be released today at 5. So like most of them, you have solutions. The only things that are gonna be like, we needed to write were like this little question or the functional group ID. And then the last one was like drawing this. Okay. Yeah. So yeah, it's a trade-off. Normally I try to do the annotated, but. Yeah. Tate, not Taft. No, Taft. Taft, Georgia. Okay,
I have, is it okay if I ask you?
yes, please.
So, this is about one of the energy diagrams. And I was just a little bit confused. I used all my attempts on it, but figured I'd ask about it anyway. So, at first I thought it would be,
Sorry, can you go to the question? Says. Identify the point of the graph with this font. Okay,
so since the CH3 is like paired between two CH3s, I thought that was bad and it would be 2. But that's not
well,
true.
first, before doing that, is it a staggered conformation or an eclipse conformation?
Staggered.
Yeah, because they're kind of in the windows between each other.
Mhm.
Which is higher energy, staggered or eclipsed?
Eclipse is higher energy.
Totally. So 2, 4, and this one on the end are all gonna be the eclipsed ones. And the staggered ones are gonna be 1, 3, and I guess this is 5.
Okay.
So that's where to start. And then here we see this has 1 Gaussian interaction, 2 Gaussian interactions. Are there any other ways that we could rotate this where we could minimize those Gaussian interactions?
If we had it like either here or here.
Yeah, totally. So here, if this is the one that's slightly higher of these 3, then it's going to be 1 because it has more Gaussian interactions, but still these lower energy staggered versus the high energy eclipse.
Okay, that makes a lot of sense.
Totally. I would say generally speaking, start with is it staggered or eclipsed, and then within that start counting things.
Thank you very much.
Totally. Is this the group that wants to hear D, or
Yes.
your name is Katie and you have a question? Work. Because of what rule? Ping pong. Okay. Part D is a little weird. Circle all of the bases that will deprotonate tetrabromophenols or whatever, that will deprotonate this, but will not deprotonate this. So we said that this is a stronger acid, right? So we want a base that will only react with the stronger acid and it won't react with the weaker acid. That's essentially what we're doing. And to do this, what we need to think about is the pKa's, right? So if it will deprotonate tetrabromophthalein, whatever, we know that the pK, we're going to need to do 10 to the something minus something for the KEQ. And we want this whole thing to be equal, greater than 1 to be product favored to say it will deprotonate, right? Well, if here tetrabromophenols, whatever, that's going to be the reactant acid. We are going to do something minus 9.5 has to be greater than 1 in terms of the size. And so another way to put it is we want x minus 9.5 to be greater than 0 if we want to get rid of those 10 powers. Now I know that's a lot of kind of like mathy jargon, but basically we have to look at these and say, okay, which of these conjugate acids has a pKa of greater than 9.5? Oh, wait, I'm so sorry. I messed up. 9.5 is this one. We're talking about tetrabromophthalein, which is this one, which has the pK of 7. Sorry. So this should be blank minus 7 and x minus 7. So what we're asking ourselves at this point is which of these 4 molecules has a conjugate acid where the pKa is greater than 7. So like the pKa of the conjugate acid of H2O is H3O plus, which is like -2. The pKa of this conjugate acid is what? If this is the conjugate base, the conjugate acid, we're going to put a hydrogen, right? So it's going to be like this. And it's just going to be an amine, which I think is 38 on the chart. Here, this is an alkyne. If we add a hydrogen on it, then I think is the value on the chart like 25-ish for an alkyne. Yeah, 25. Cool. That's how I said I'll need to memorize that. I'm like, I guess I have these memorized. And then this nitrogen, if we add a hydrogen on it, it's NH4 plus. And what's its pKa? 9. So that's the conjugate acid strength there. And this one, we don't quite know. But I'm going to tell you, what do you want to guess? Do you want to guess that this is a more stable conjugate base than something neutral? No. So this is probably going to be higher than 9, right? And we see that, hey, if our thing goes from a negative charge to we protonate it and make it neutral, like all of these do, then it's probably going to be in like the 25 to 38 range. So I would guesstimate around 20 to 30. So which of these values, because we know that these two, when you protonate them, their pKa of the conjugate acid is 25 and 38. Because we're going from negative to neutral, and neutral is more stable. So this one is going to do a similar thing. So we're going to guess probably 20 to 30. So now the question is, which of these -7 is positive? Yes, so we can eliminate this one. That's half of it. The second part of the question is, we do not want to deprotonate the original molecule. So if we do another one of these, 10 to the product minus reactant, we want to not protonate, so we want it to be less than 0. So in this case, we have the acid over here is going to be 9.5, right? And that's going to be the reactant acid. And then our mystery base is going to have the product conjugate acid over here. It's kind of like we're substituting each of these molecules in for this OH. And we're asking which of them will react with this, but will not react with this. So another way of writing this is x minus 9.5. We want to be less than 0. So which of these numbers, if we subtract 9.5, do we get something negative? Only the last one. So the only thing that is going to deprotonate this one with all the bromines, but not deprotonate the original, is this one. That's a much harder question. Hi. Sorry? Oh, no, I haven't seen one, sorry. But
And
feel free to look around.
why was it both less than 0 and greater than 1?
Because this is KEQ. So if the KEQ, and I should say not less than 0 here, this one's less than 1.
You know that
So if the KEQ is less than 1, it's reactant favored. And the KEQ is greater than 1, it's product favored. See, this is the thing where I didn't want to do it because they're like mental gymnastics. The other way to think about it is like, which of these has a conjugate acid whose pKa is between 7 and 9.5? Like that's another way of doing it. But if I just say that, you're kind of like, why? When I do it this way, it's harder to follow, but like it's connected to this kind of conjugate acid over here. Starting molecule is either this one or this one over here, acid, and we use the KEQ form. Because we do want it to deprotonate this. So we want this reaction where we put this bromine guy here and our mystery base. We want it to be product favored. So we want the KQ to be greater than 1. And so what that means is we want x minus 7 to be greater than 0. Verse, we do not want it to deprotonate this. So when we have this one and a mystery base, and then the conjugate acid over here, we want it to be less than 1 because we don't want it to deprotonate. Yes, it's a lot. I hate that question, which is why I don't do it normally. Yeah, come over. Oh, thank you. I appreciate that.
Well.
It's a rough thing. Like doing a 3-hour lecture is hard. I get to deliver the final lecture of the course, which I'm very excited